Okay. So I don't know why this is. Okay, maybe it will vanish slowly. Okay. So this so we'll so linear algebra is sort of we study vector spaces and maps between them. Yeah. So I'll start with the definition of vector space. But do you know what a field is? Yeah. Yeah, so field is some set together with addition and multiplication satisfying certain axioms. Yeah, so so field is this triple k plus dot where where plus and dot are binary operator on the set k satisfying some axioms. Yeah. So I'll not write down the axiom because I assume you know what fields are. Yeah, so you can do multiplication and addition, and there is one, and every non-zero element is inverted. So there is the additive identity which is zero. There is a multiplicative identity which is one, and every non-zero element is invertible. And then there is distributive law, associative law, commutative law. All these laws are there. Yeah. So so vector space is. So since you have seen linear algebra before, I'll do the vector spaces over a general field to start with, yeah, and maybe later on we'll concentrate on some over reals or complex as over complex numbers or something algebraically close. But to start with, let's define things over a general field, yeah. So what is a vector space? So definition. Um, a vector space V over a field, a vector space, or maybe let's write it this way, a vector space over a field K is a pair, or maybe a, a triple, one can say, yeah. So V, so, um, so yeah, why doesn't it write anymore? Something went wrong and stopped writing. Okay. Yeah. A vector space over a field K is a triple V plus and then a scalar multiplication, which I'll right now denote by dot, but later on that dot will disappear. Yeah. So where V plus is an abelian group. Abelian group, and then there is a scalar multiplication. Yeah. So and, and so I'm trying to sort of, so if you write down so you know what an abelian group is, yeah? So that means if you take any two elements in V, so there is a additive identity 0, and any two elements you take, the sum is also in there, and so that's a group. So it's a group and it's commutative, yeah? The addition is commutative. This is what an abelian group. And so and for all alpha in K, and So this dot is sort of a, yeah, so maybe I should write it this way. Yeah, so the dot, yeah, maybe I shouldn't have taken, but anyway. So dot is an operation from k cross v to v. So it's a function, yeah, from k cross v to v. So it is alpha comma v. We will denote it by, it goes to alpha dot v. Yeah, satisfying some axioms. Yeah. So for instance, alpha beta uh, dot v is so satisfying these axioms. Alpha beta dot v is alpha dot beta dot v, and secondly, this distributive laws, alpha plus beta. So this sum is in the field. Yeah. So we are using the same notation for plus, but from the context, maybe you can figure out. Yeah, this is same as, and same multiplication as in field. Yeah, but from the context, you can figure out whether it's a multiplication of a scalar to a vector, or whether it's a multiplication in the field. Yeah. So alpha dot b plus beta dot b. So this is multiplication of a scalar on a vector. Here, this alpha dot beta was sort of multiplication in the field, and here the addition is in uh, in the field, and here the addition is in the vector space. Yeah, on the right hand side, the addition is on the vector space. And then there is another third law is sorry, the other distributive law is alpha v plus w, or v plus v prime is alpha v plus alpha v prime. It used to write better than there's something. Okay. And then there's one dot. So the fourth condition is, so there is another condition that one dot v is equal to v. So here alpha beta are in k, and so this holds for all alpha beta in k, and v prime in v, and one is the identity element, the unit element of the field k. Yeah, so one is in k. One is the unit of k, unit of the field. Yeah, so it makes sense over not just real and complex numbers, over any field. So I don't know how much fields you know, but if you're familiar with other fields, then it will work over any field. But if you're not that familiar, just think of it as real or complex numbers. K is either set of the field of real numbers or complex numbers. Yeah. So this is what a vector space is. Okay. Um, so so what are some examples of a vector space? So K with the own addition and subtraction is for example a vector space. K plus dot is a vector space over K itself, over the field K. Yeah. So this is the first example. You can actually maybe one can say the zeroth example is v equals 0. Yeah, it consists of only one set, one element, 0. It's an abelian group of consisting of the only element, so the trivial abelian group, and then everything. So scalar multiple, etc. Everything, whatever you multiply with 0, you get 0. Yeah. So you can check all these axioms will be true. So it's also a vector space. And then, of course, since you are familiar with vector space, you'll also know that if you take k power n tuples of k. So So somehow it's K power n is a vector space, and so, so so I don't know why it's acting so funny. Sometimes it stop writing altogether. Um, okay, let me try one different software. Yeah, because it's not writing. Okay, now it just started writing suddenly. Yeah. So okay, so hopefully this will continue. K power n is a vector space. Where so you can think of it as n tuples, yeah, and the scalar multiplication is component wise. Okay. Okay. Again, it has. Let me try a different software. Yeah. So this is not working. Let's try to change a little. Um, there is a previous version of OneNote which sometimes works better. So let's see if I can get that works better. Then we'll do that. Um, okay, that page is not coming, unfortunately. Yeah. Why is this page not coming? Slash linear algebra for books. Uh, so it used to work properly. I'd given many online courses during COVID, but somehow it's creating some trouble today. Okay, anyway, let's try again. Yeah, with the same setup. Let's see. Hopefully things will become better. Okay, let me share again. Okay, let's see if it works better. Um, so Kn is a vector space. So let's see. Draw content with component wise at. Okay, yeah, with component wise scalar multiplication. Okay, if this works this way, we'll be in good shape. Yeah. So so these are some examples of vector spaces. So you can, I mean, there are many natural examples as well. Yeah. So you can consider, for instance, polynomials. Polynomials with coefficients in k or r or something. Yeah. So po polynomials uh, over 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 r, let's say. So if you consider two polynomials, you add them, you get another polynomial. Yeah. Or if you do a scalar multiplication, you get get another polynomial. So polynomials over r or c, or for that matter, over any field. Any field. So any field. Yeah. So this is these are also, so you can take continuous functions, for instance. Those are also going to be continuous functions from r to r to r, let's say. Yeah. Or in fact, from any topological space to r. If you take these as continuous function, then that also forms so if you add two functions, then it's again, so adding this, you are taking real valued functions, right? So adding two functions makes sense. So sum of two continuous function we know is a continuous function, and so on. So continuous function is also uh, the set of continuous function. Real valued or complex valued will also be be a vector space. So and so on. Yeah. So I mean, but we will see mostly Rn and Cn and so on. These are the typical vector spaces we'll see, but they occur naturally. So you can also consider polynomials of degree at most n. Yeah. So maybe sub example. So sub example is so polynomials of degree at most some number at most n. Yeah. Some n greater equal, even you can take 0, but then it will be the trivial vector space. So you know that if you take sum of two polynomials, the degree doesn't go up. Yeah. So if two polynomials have degree less equal n, then their sum is going to have degree less equals n. Yeah. So this is also a vector space. So these are some examples of vector space. Okay. So so far, any questions? Okay, so I suppose things are clear. So, um, or maybe I can write a little more on this panel, and then I'll make it smaller. Okay, so 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 now we'll study some things about vector space. So to a vector space, so for instance, we can associate something called a basis. Yeah. So are you familiar with basis of a vector space? Yeah, so basis is so there are many ways. So basically, what we want is a collection which will generate our vector space and so on. Yeah. So before I define basis, we'll have to define what a linearly independent set is and so on. Yeah. Uh, so maybe let's call it a definition. Let S be a subset of V, where V is a vector space. Then S is called linearly independent. So I'll abbreviate it as Li. If um, if we take any element, so any collection in so if for any any n greater equal 1 and any distinct V1 to Vn subset of S. So maybe I shouldn't put a bracket here. Yeah, so let's see. Yeah. So any V1 to Vn in S, mm, mm, uh, uh, um, summation or so instead of summation notation, let's write in the full notation. A1 V1 plus An Vn equals 0 for Ai is in K, I between 1 and n. So V is a vector space over K, yeah? Implies A1 equals A2 equals An equals 0. So all the coefficients are 0. Yeah? So this is what a linearly independent set looks like. So if S is finite, say S contains V1 to Vn, then you can just specify that this last line. So if S is precisely V1 to Vn, then you just say that it's linearly independent if this happens, last line happens. A1 V1 plus An Vn up to An Vn is 0, then Ais must be 0. Yeah. Um, but if S is infinite, then this is how you define linear independence. Okay. And if a set is not linearly, a subset of V is not linearly independent, then you say it's linearly dependent. If not linearly independent, then it is called dependent, linearly dependent. Yeah. So linear independence is more important. That's why we define linear independence. And then otherwise, you can also say a set is linearly dependent if one of them you can write it as a linear combination of others. And then say it's linearly independent if you can't do that. So that's another way of talking about linear independence. But I suppose you are familiar with these notions, so I'll not delve into it too much. Yeah. So So for instance, but maybe since it's the first class, let's do one example. So in R2, yeah. Um, um, can um, so 1, 2, 3, 4. So is this set a linearly independent set? Maybe one of you can answer.
Yes, it is.
It is a linearly independent set, right? So why? What you can check is that I mean, if you want to sort of make linear combination of these two zero, then the coefficient of the first one should be negative 3 times the coefficient of the second one. Yeah. And if you do that, then it turns out that it is it will the second term will not become zero. Yeah. So this is linearly independent. How about if I add one element, 1, 2, 3, 4. 3, 4, 5, 6. Is this a linearly independent set? Yes or no?
No, this is linearly dependent.
This is linearly dependent, yeah? So why is it linearly dependent? So I guess you may have seen some theorems, yeah. So the R. This is sort of two-dimensional vector space, and we have taken a three space. So those who have seen some linear algebra, you know that this is a two-dimensional vector space. So we'll define all this in a bit, but and we have taken three vectors, so it has to be linearly dependent. But you can actually find a relation, yeah. So let's see. So maybe can someone cook up the relation quickly? So you can actually take any two and try to write the third one as a linear combination of that thing. So yeah, so maybe one can do this. Yeah, 1, 2 plus 5, 6. How much is it?
2 times 3, 4.
This is 6, 8. Yeah, which is 2 times 3, 4. Yeah. So now you have a linear relation between these three. Yeah. So it can't be linearly independent. So it's not linearly independent. Okay. Okay, so I'll assign some homework problems on how to check something is a linear independence or not, which might be more like a review for you guys, rather than delving too much on what linear independence means. Yeah, so I think most of you may be familiar with it. So I'll go to the next step to define what a basis is. Yeah. So to define what a basis is, so there are many equivalent ways to define what a basis is. So I'll is it somewhat visible? This, if I keep it, is it useful or it is not visible at all?
It is visible.
It is visible. Okay, so it is somewhat useful. So let me keep it this way. Yeah. So so this has become a bit thin. So let's just go to the next thickness theorem. Yeah. So let V be a vector space of over K, a field K. Okay, in my notes is okay, but anyway, it doesn't matter. So we will think of Um, uh, yeah, so should we work with infinite sets? Yeah, so let's think of this possibly infinite dimensional vector space, because since you're masters and now PhDs and maybe do PhD, so maybe one should do some more advanced stuff. Yeah. So let S contained in V uh, be a subset. Then the following are equivalent. Um, S is a maximal linearly independent set. Yeah. Which means that if you add any more element to S from V, then it becomes linearly dependent. That is what this statement means. Yeah. So there is no bigger set than S, no set S prime strictly containing S such that is linearly independent. Yeah. Second is uh, S is linearly independent and generate and generates V. Yeah. Three is every element of V is uniquely written as every, so V for all V in V, there exist unique uh, um, subs. There exists a way to write V, so and it is unique. Yeah, so maybe I'll write it this way: A1, uh, V1 to A and Vn, where AIs are in the field K and VIs are, where VIs is in the set S. Yeah, I between 1 and 10. So, and maybe AI is non-zero. So yeah, since I'm insisting AI to be, so V non-zero, let's just be more precise. Yeah. So zero, of course, you can write it. So if you allow AIs to be zero, then this won't be unique. Yeah. Then you can always add any other vector and add zero. Or you think of uniqueness in the sense that it's unique in the sense that the coefficients which are zero, you can ignore them. Yeah. You can think of it as unique, or you can think of it as this way, one way or the other. Yeah. And four is S is a minimal generating set. So so I didn't say what a generating set means, and I used twice what generates mean. So I suppose you know what a generating set, yeah? So S is said to be a generating set if no, of V if you take a linear combination of elements of S, then you get whole of V. Yeah, every element of V is some linear combination of elements of S with coefficients in the field K. Yeah. So is it okay if I don't write the definition of generating set? Yeah. So these four statements are equivalent, and then I didn't mean to do this. So these four statements are equivalent, and um, when all the four are true, then we say that this is a basis. Yeah. So, so S. So definition. So we'll show why these are equivalent. S is called a basis if it satisfies basis of V, if it satisfies these equivalent conditions. So if it satisfies one of them, then it will satisfy all of them. Yeah. Conditions. Okay. So the proof is pretty straightforward. So okay, so maybe okay. So let's see. So one implies. So maybe I'll just sketch out a proof. So one implies two. So of course, S is one says that S is a maximal linearly independent set. So the first part S is linearly independent is obvious, yeah. So we only have to check it generates V, yeah. So so that part is also clear, right? So let V be in V, so and then um, then if it says unstable, you are still able to hear me, yeah?
Yes.
Yeah, okay. Then V, you can write it as or and then so say if V uh, does not belong to is not a linear combination. Yes, combination of elements of S, then what do we know? S union V is linearly independent. Yeah, because S was already linearly independent if V is not a linear combination of S union V. So maybe this will follow from one of the homework problems if it doesn't. So if you can't write V as a linear combination of this, then um, then then this will again be linearly independent, because if you have a linear independence relation, the coefficient of V must be non-zero, because if that is zero, then S will become linearly dependent, but we are assuming S is linear. And once the coefficient of V is non-zero, you can move V to other side and divide by the non-zero coefficient. Because you're in a field, so any non-zero number you can divide by it. So V you can write it as linear combination of other elements, yeah, which will contradict your hypothesis, right? So contradicting one. So contradicting one. So that tells you that hence two holes. So what we have shown is any element of V can be written as a linear combination of elements of S. So that is what precisely 2 is. Yeah, 2 says that V is linear. S is linearly independent and generates V. Yeah, so that's 1 implies 2, and now 2 implies 3. So of course, since S generates V, every element you can write it as linear combination of these guys. Yeah. So you can always write any element V in V as linear combination of these guys. You only have to check that is unique. So for uniqueness, you'll use linear independence. Yeah. So 2 implies 3. So okay. So maybe so B is in B. Since S generates V, you can write it as A1, and let's say V is non-zero. So then V1 plus A and Vn. And of course, you can omit things which has zero coefficient, yeah? Where VI's are in S and AIs are in the field K for I between 1 and n, and AI is non-zero. Yeah. So this is clear by generation. And suppose you have another description. V is also suppose so now for uniqueness. Suppose V is also B1 V1 prime to VM prime, where uh, V1 prime to VM prime is in S. So possibly different elements of S, yeah? And BIs are some non-zero elements in the field K, I between 1 and M now. Right? Then what you do is you take the difference, right? So, so and uh, so you sort of, yeah, so you take the difference and so, yeah, so now maybe you sort of merge these two sets, yeah, V1 to Vn, and so maybe, yeah, so to write things formally, it requires a little more effort. So let's just write this union, V1 to Vn, um, W1 to Wm, sorry, V1 prime to Vm prime. Let's call it, so let's call this, yeah, W1 to, so it's possibly a bigger set. So if I had a finite set, then S was finite, then it would have been easier to write. So maybe W1 to WL, let's say, yeah. So this union, I'll denote it by W1 to WL, and the coefficients, maybe I'll change it. Yeah, so let's call it AV1 to AVN. Yeah, so these are AV1 is a coefficient of V1, and AVN is a coefficient of uh, VN. And this also so maybe I'll change it a bit so that it becomes easier to write. Yeah, AV1 prime to AVM prime. Yeah, so it's just the coefficient of the vector involved, right? So that in the next line it will be easier for me to write down. Yeah, so AVI is in K, and similarly AVI prime. So it's just the coefficient of the vector in the expression for V. Yeah. So now what we get is, if you take the difference of these two equations, so you get 0 equals um, A uh, so maybe I should call this B instead of A. So everything is A, then it won't work. Yeah. Then we are repeating it. So let's call this VI prime. Yeah. So now if I take the difference, then it is A W A. So the first expression has A's and the second expression has B's. Yeah, so this is B's. Yeah. So now if you take the difference of 1 and 2, so you get on the left hand side, you get 0, and on the right hand side, what do you get? AV1 minus BV1. So BV1 may be 0, yeah, because if B1 doesn't appear on the right, then it will be 0. But if V1 appear on the right, then it is whatever it is, yeah. So this may be 0, but it doesn't matter. Yeah. But instead of V1, I'll use W1 to WL. Yeah, that is the union of these two. Right. So W1, W1. So so some of these may possibly be zero. Yeah. So you declare AWI to be zero if WI does not belong to V1 to Vn. Yeah. And similarly, BWI to be zero if WI does not belong to V1 prime to Vn prime. And then if you write this way, I hope it's making sense. Yeah. So let me know if you have questions. Yeah, so this identity you'll get. So that will tell us. But you see, this is W. This is a subset of S, which is linearly independent. Yeah. So we are assuming two, right? So two says S is linearly independent and generates V, and we are trying to show unique expression, right? So this tells. So now it tells you that AW1 WI must be equal to BWI. BWI for I between 1 and L. Yeah. So for all so this in particular shows that I mean these V1 to Vn and V1 prime to Vm prime, they are all same. Up to permutation, they are all same, and their coefficient is also same. Yeah. So that tells you that that proves the uniqueness of hence hence um, the expression for V is unique. V is unique. Okay, is this okay? Make sense? Yes, everyone? I mean, if you had seen only for finite dimensional vector space, what you could do is say it can be written in two different ways. Then you take the space generated, the union to be this thing. Then you can write V as summation AI WI, yeah, and then use and BI WI, two ways, yeah, and then take the difference, and you'll see that this is unique. But anyway, we know that it's going to be unique. So this L is also equal to N is same as M. Yeah, so it's all same. Okay, so this proves 2 implies 3, and then let's yeah. So let me move this a bit. Okay, the scale is not helping me. Okay, but anyway. Now 3 implies 4, and then 4 implies 1 is what is left, yeah? So okay. Yeah, so let's try to do 3 implies 4. Ayo. Uh, I think they've changed. I haven't used this software since COVID, yeah? Now, since the online classes stopped. And they've changed this, so things work a little differently now. So, see, this is... yeah. It doesn't allow me to do this variable thing. And I thought this is beneficial. Okay, let's try. Okay, it looks like it's not going to allow me to write it in if I minimize it. Yeah. So let's keep it a little bigger and see if it works. Three implies, yeah, it's working now. 3 implies 4. Now we want to show that if things are uniquely there, then S is if you can represent every element uniquely by every element of V uniquely as linear combination of elements of S, then we want to show that S is a minimal generating set. So by hypothesis itself, it says that S is a generating set because you can write every element as so S generating set is okay. Okay, yeah, and then we want to show that it's minimal generating set. So that will yeah, so if you drop something, then that element basically you can't write. Yeah. So uh, um, yeah, so how do I uh, yeah, so um, so let's say S prime is some proper subset of S. Then we want to show that it doesn't generate S, yeah, and V belongs to S, yeah. Then of course V is equal to V. That's one expression, and yeah. So this is also straightforward, and sub and suppose sometimes it stopped writing. Suppose maybe I should write in advance a little bit. That may help. Yeah. And suppose um, uh, V belongs to the span of V S prime. Yeah. So, so we are assuming, so suppose it's not a minimal generating set. S prime is smaller than S and it generates whole of V. Yeah. So then you can write V also as summation AI VI, where maybe some, what happened? Are you with me? Can you see the screen still? No. Okay. So yeah, that is what may have gone wrong. Yeah. Is now you can see?
Yes.
Yes. Okay. Good. So so where AIs are in the field K and VIs are VIs are in between 1 to n is in the set S prime. Yeah. Then it contradicts our um, R3, right? That is uniquely contradicting 3. The uniqueness of every element of V. So there are two ways an element of V, in fact, an element of S you have written. Yeah. So you take V in not just S, but S minus S prime. So this is what I meant. You take V in S minus S prime, then it will work out. Yeah. So so there are two ways of writing it, this and this, which is a contradiction. Yeah. So that covers 3 implies 4, and finally we should prove 4 implies um, 4 imply, now we should prove 4 implies 1 and we'll be done. Yeah. Going a little slow, but it's okay. So next time maybe I'll write a little bit in advance so that things become easier. Yeah, sometimes it's difficult to write on this. So 4 implies 1 says that if S is a minimal generating set, then S is also a maximal linearly independent set. Yeah. So we want to prove that if S is a maximal linearly independent set too. Yeah. So maybe yeah. So let's try to prove that it's linearly independent, and then maybe we will show that it's maximal linearly independent. Yeah. So suppose S is linearly dependent. Yeah. Suppose S is linearly dependent, then what will happen? We can find. Yeah. So suppose there exists. So suppose A1 B1 to A and Bn is equal to 0 for AIs in K. Yeah, things are legible, right? You can read it comfortably. Yes, okay. And VIs are in S. Yeah, I between 1 and n. So suppose this happens. Then we want to show that AIs must be all 0. Yeah. But so say A1, so some AI is non-zero. So say A1 is not equal to 0. See, so you can assume one of the AIs is non-zero, and then we'll get some contradiction. Yeah. So say A1 is non-zero. You can assume any AI, but let's say A1 is non-zero. Then what happens? Then you can write V1 as negative of 8 A1 V1 as negative of 8, or maybe just V1 as negative of A1 over A2 over A1 V2, negative of A3 over A1 V3, and so on. Negative of AN over A1 VN. Yeah. So that tells you that S is not a minimal generating set. Yeah, because V1 you can write it as linear combination of V2 to Vn. Then of course, if you remove V1 from S, then still a generating set. Yeah. So S minus V1 is also a generating set. Why? Because you take any expression for any element in V, and wherever V1 appears, you replace it by this expression. Yeah, and that gives you a new expression for V. Yeah, with which involves only elements of S minus V1. Yeah, so this contradicts 4, contradicting 4. Yeah. So hence that proves that you can't have any coefficient non-zero in this expression. Yeah. So hence S is linearly independent. Okay. And now we want to say that it's maximal linearly independent set, but that is okay. That is obvious, right? Because S is maximal linearly independent set. Why is that? Why is it maximal? Because it spans whole of V. Yeah. So if you add anything, then it will not be linearly independent. Yeah. So because S generates. So the fourth hypothesis of 4 is that it's generating set of V. Yeah. because S generates V. So if you add anything if you include any more element in S from V, then it won't be linearly independent. Yeah, because that element can be written as linear combination of some elements. Yeah. So this completes the proof of this equivalence. Is that okay? Seems reasonable to everyone? Yeah. So maybe things are going a little slow. Is it going a little too slow? Then I can pace up a little bit. If it is going at the right pace, then that's good. So maybe you can email me your feedback. I'll I'll maintain. I'll send. I'll give you my email ID and I'll give Vivek my email. At least I have his email ID. So I'll give Vivek my email ID and my phone number as well, which he can share with you guys. And if you have any concerns, you can email me. Yeah. Okay. So this. So we have defined what a basis is. Now. So I'll share these notes as well. So you don't have to worry about the notes that much. I'll just make I'll just copy paste and share these notes as well. But of course, it's part of it is not very. My handwriting is not that good. So, but anyway, there will be something for you guys. Yeah. So let's see some consequence of this result. Yeah. So let me see if I have a similar size. Yeah. So let's keep this similar size. It used to be much. I think the previous version was much better. I'll try to use the previous version next time. Previous version of on OneNote, they sort of ruined it. See, I can't really. It's not even moving. So I don't know. Or maybe I'll have to use some other software. They've destroyed it. Okay, anyway, let's just try to get somewhere. Okay, so so what was happening? Okay. Okay. So let me write here. Yeah. So corollary of the results which we have proved. So so or maybe there's some argument which is needed. So more or less it's a corollary. Every linearly independent subset of V can be extended to a basis. For that, I'll have to prove existence of a basis. Yeah. Okay. So I'll do that. Yeah. Extended to a basis of V. Okay. So this is one. Second, so this will in particular prove that every vector space has a basis. Yeah. Every generating set of V can be shortened to a basis of V. And is there some third statement? Yeah, maybe this is where so maybe these two first we can think about. Yeah, so let's try to prove this. So see, if it's a linearly independent set, you can keep adding. Yeah, and even so, if it was a finite set, so if the vector space was finitely generated, after a certain number of times, it has to become, so it more or less immediately follows from the previous thing that it will become a basis. Yeah, it can't go on forever if it is finitely generated. If it goes on forever, then that means that it's not finitely generated. Yeah, so there is. And the second one also, if you are given a generating set, then there is a subset which is a finite generating set. Then there is a subset which is a minimal generating set, and that minimal generating set is your basis. Yeah. So these problems occur only if V is not finitely generated vector space. Then only one has to argue a little bit. Yeah. So then the problem is somewhat set theoretic. Yeah. So do you know what axiom of choice is or John's lemma is? Yes, John's lemma everyone is familiar with. Yeah. So you can use. So maybe this I'll leave it as an exercise. Yeah. So for infinite thing, I'll leave it as an exercise. So use John's lemma. So this may be homework. Yeah. Use John's lemma to prove that every so to prove one, and once you have proved one, then two is basically a consequence of one and the previous theorem. Okay. So maybe this corollary itself is a homework. Yeah. So you try to use this theorem. So John's lemma or axiom of choice, these are all equivalent to set theoretic statement. So you try this homework. If you can't do it, then we will discuss it in the next class. Okay. Okay. So now what we want to do next is show that any two bases have the same cardinality, and that will allow us to prove that or define what a dimension of a vector space is. Yeah. So again, for when the vector space is not finitely generated, then the argument requires a little bit of set theory. But otherwise, if it is finitely generated, then the proof is slightly simpler, is straightforward. And so let's do the finitely generated case, and then we will worry about the infinite one. Yeah. So to prove any two bases has the same size, there are various proofs. One proof is also using matrices, but I'll give you an abstract proof. Yeah. So there is this trick called exchangeable trick. Yeah. So what you do is you start with two bases and you try to replace one element of one basis by another element and so on. So all this trick, when you try to write it in a simplified way, you end up doing the following. Yeah. So let V be a vector space. Okay. And B and let's take two sets. Yeah. B1 equals V1 to Vn, and B2 equals and let's call it Wi's, yeah, instead of primes. V1 to Vn and W1 to Wm. Yeah. B two bases of V. Okay. So so we want to show that M equals N eventually, but oh, yeah, I'm trying to tell you what exchangeable. Yeah. So sorry. So so for exchangeable, maybe I'll rewrite this proposition. Yeah. So exchangeable trick statement is somewhat different. Different. So B1, let no. So this was yeah. So okay. So let B1 be linearly independent set. So you don't really. Uh, so this is maybe exchangeable trick lemma, you can call it, and B2 is a set consisting of more than n elements. Yeah. So let's say n plus one element. W1 to Wn plus one. Yeah. Be a linearly independent set. Yeah. So here you have Bn. So B1 has size n and B2 has size n plus one. Then the conclusion is there exists one Wi such that B1 union that Wi is also a linearly independent set. Yeah. So the claim is for for some I B1 union Wi. I mean, so uh, this rather this list of elements, yeah, V1 to Vn Wi is linearly independent of length n plus one. Yeah. So in this sense, I'm not going to, so if one of the Wi's is same as Vi, I'm not going to include that. I'm going to make start with V1 to Vn and include one element which is not in V1 to Vn and make a linearly independent set of length n plus one. Okay. So this is what the exchangeable trick lemma is. So how do you prove this? So the point is, um, uh, uh, if any of these Wi's does not belong to the span of V, then we are done. Yeah, we'll take that Wi and it will become a linearly independent. So if Wi does not belong to span of V1, then done. Yeah. So that is what does not belong to. Then basically take Wi as your guy. Yeah. And if all the Wi's belong to a span of, so we will show that it can't happen that all the Wi's belong to span of this thing. Yeah. So suppose this W1. So suppose this whole set B2 is contained in span of BIs. Yeah. So span of B1 contained in the span of B1. Yeah. Then we want to show so then we will show there is some contradiction. Yeah. So what will happen is we'll get that WIs are linearly dependent. Yeah. So so what do we get? So we get W1. We can write it as some. So WI we can write it as summation AI. Um, uh, um, yeah. So maybe yeah. So it's exchangeable trick. So I'll have to use some. Yeah. So what we get is this W1 V1 to Vn. This is linearly dependent. Yeah. Because W1 belongs to the span of B1, so we get that this is linearly dependent. Yeah. So um, so we can write um, um, so in the expression for W1, so there is a linear combination AI uh, Vi plus some A W1 is equal to zero is equal to zero for A not equal to zero, and because if A is zero, then VI's will be linearly independent. Yeah. So A not equal to zero, and since A is not equal to zero, so one of these AI's must be zero. Yeah. And AJ not equal to A AJ not equal to zero for some J between 1 and 10. Yeah. Okay. So what we'll do is we'll drop that VJ. Yeah. So um, so what we get is that this W1 V1 VJ minus 1 VJ plus 1 to Vn. Yeah. The span of this. So if you look at the span of this, uh, um, so Vj will belong to the span of this, because Vj is going to be linear combination of W1 and the remaining Vi's. Yeah. And Vi span the whole. The span of this is same as the span of uh, V1 to the span of B1. Yeah. So it is the same as the span of B1. Yeah. Because it can. I mean. This W1 to W1 V1 to Vn, this span is same as the span of B1, and we have removed something which is a linear combination of other guys. Yeah. So this is again the same as the span of B1. Yeah. Okay. And hence so now if we consider, so now again see, this whole of B2 belongs to B1. Yeah. So now if I consider this set W2 W1 V1 Vj minus 1 Vj plus 1 to Vn, this is again linearly independent, again linearly dependent, right? Because V2 is a linear combination of these guys, yeah. I mean, these guys span whole of V1 and W2 belongs there. Yeah, so W2 you can write it as linear combination of other guys. So this is again linearly dependent. And again, if you look at the expression of W2, so again, if you write, so it's linearly dependent. So you can again write it as maybe let's write it this time somewhat differently. So uh, B1 W1 plus B2 W2 plus A1 V1 plus AJ minus 1 VJ minus 1 plus AJ plus 1 VJ plus 1 up to A and Vn is equal to so you'll get these zeros where B1 is certainly B2 is certainly non-zero. Yeah, because B2 was the new guy. Yeah. So uh, and and uh, and this W1 to V1, the remaining VIs were linearly independent. So one of these coefficients must be non-zero. But remember, even W1 and W2 are linearly independent, right? So one of these ages, so again, you can argue that one of these ages is non-zero. Ages is so some other so AJ1 maybe was this thing. So some other AI is non-zero. Yeah, so let's keep this. So some instead of so some AI is again non-zero for some I. Some I. Yeah. And then again you try to then again you can replace that VI and add another W3. Yeah, so keep going this way. And what you'll get is that eventually Wn plus 1. So if you keep going this way, you'll keep on adding and you'll get this new set Wn is linearly dependent. Yeah. And this is a contradiction, yeah, because you started with the hypothesis that okay. So if you continue this after n plus 1 stage, after n stage, you will get this. All the VIs will be gone, and only this WIs will remain, and you'll get that this is a linearly dependent set, which will be a contradiction. Yeah, so this is what exchangeable trick is. Okay. So from here you can, so now you can prove that any two bases it has the same, okay, so there's still time. So corollary is that if V1 and V2 are two bases of a finitely generated vector space V, then size of V1 is equal to size of V2. Okay. So before going to this corollary, maybe is this clear why one of these AIs will be non-zero? See, if all the AIs are zero, then that will tell you that W1 is linearly dependent with W2. Yeah, so that can't happen. So one of the AIs must be non-zero. And once one of the AIs is non-zero, you again replace that VI. Yeah, VI, because you can write that VI as linear combination of other guys. So you can remove it and the span will not change again. It will be same B1. And then again, you take W3, yeah, and include it and keep doing. Okay. So the new B3 is not going to be zero. So again, the coefficient of that W3 is not going to be zero. Then again, one of these, so it can't happen that all the AIs again are zero, because that will disprove, that will contradict the linear independence of WIs. So, and you can keep this process. Yeah. So I hope this is clear, but if it is not, you can feel free to ask me questions. Yeah, interrupt me and ask me questions. So why is the two sides same? So say B1 is V1 to Vn, yeah, and B2, the size of B2 is greater than n. Then of course um, there will be n plus 1 elements, and um, um, so then of course this tells you that you can find a linear then by above corollary, above trick, um, V1 to Vn, and say B2 has elements W1 to Wm. Some number, yeah, Wm, m greater than n. So in particular n plus 1 elements, then you can find something, some W1 such that this is linearly independent of length n plus 1. Yeah, which but B1 is the minimal is the maximal generating set. Yeah, so you can't have a bigger, or it's a linearly independent set. So yeah, so it's also a maximal generating set. Yeah, because it's a basis. It's a minimal linearly independent set. Yeah. So B1 is a minimal linearly independent set, but now we have found a bigger linearly independent set. Yeah. So which contradicts. Yeah. But uh, so I don't know what happened here. Now again, I stopped writing. So, length. Yeah. But, yeah, suddenly it stops writing. So I don't know what happens, but let me restart this. Yeah, sometimes restarting helps. Restart this OneNote again. Maybe that will help. Okay. I have to share. Hmm. Okay, I still can't write it. Um, any ideas what might be wrong? I can't even write with, now I can write with a finger at least. Okay, but not with my pen. Okay, so let's try to, so let me try to do it with the, so maybe something is wrong with the pen. Yeah, maybe something is wrong with the pen. So then um, by this trick, this is, but B1 is minimal generating set, is a maximal linearly independent set. Maximal. It's a basis, right? So it's also a maximal linearly independent set. Set a contradiction. Contradiction. So contradiction to the hypothesis that B2 has more elements. Contradiction. I think this is not going to work. So I'll try to write at least a part of it, most of it, and maybe while teaching I'll go a little slow and explain you next time onwards. Because sometimes if you stop writing, then with the pen, with hands, it's a bit difficult to write with finger. So okay. So that proves that any two linearly independent set has the same size. Yeah. So thankfully now again I started writing with the pen, so it will solve my problem for now. So now the definition is that um, uh, let V be a finitely generated vector space, then dimension of V, which will denote by dim V, is the size of a is the size of or the cardinality of a basis. Yeah, and by the above proposition, we know that this is well defined. Yeah, by the above corollary. If uh, if V is not finitely generated, so if you can't find a finite generating set, then we will define dimension of V to be infinite. Yeah. So I'll just call this infinite. So in fact, this theorem which I've written that any two bases has the same size. This is actually true even if V is infinite generated. Yeah. So then one has to say so they are both infinite. So but what you can say is that the cardinality of the two sets are same. Okay. So